This lecture will discuss importing data into R. The example dataset is provided to you, and it would be beneficial to follow along with an example in R. This presentation will give you instructions on how to import data into R. Once data are imported, how to understand the characteristics of the data that were imported, and be able to review the data. And finally, some simple manipulations of data to allow further analysis. What types of data do we most commonly deal with? Excel and CSV files are commonly used to distribute pharmacokinetic data from bioanalytical laboratories, particularly during ongoing studies in order to evaluate data and inform dosing in subsequent cohorts or parts of the study. These types of files, however, can be further manipulated after finalization, and therefore, for regulatory purposes, Sas files are also used relatively frequently to transmit final study data. We will next focus in detail on importing flat CSV files. So, we have some bioanalytical data containing drug concentrations by time for a particular subject, 109, who received an oral 500 mg dose of drug X. The concentrations of drug X are measured at PK sampling intervals from pre-dose to 24 hours after dose administration. The lower limit of quantification of this assay is 1 nanogram per ml, and concentrations below this are reported as less than LLOQ, as we can see for pre-dose and the 24-hour time points. If you've not previously saved data as a CSV format, the method is similar to saving Excel files, with the exception that we select .csv file extension. Before importing data, we need to know the location of our working directory. This is the location from which R will pull data or export data if the location is not specified. We can reset the working directory using the setwd command. However, we're also able to specify the file locations to import or export specifically. As I mentioned, there are a couple of simple options to reset the working directory. We can use the function setwd and include the directory location, as done here. Or we can go to File and change directory. Alternatively, when we import data, we can specify the file location, which is typically my preferred method. Let's use the read.table function to read in our CSV file. The first argument tells R what file we want to use. If the file is located in the working directory, we can use the name of the file in quotes. In this case, our file name is named pkexample.csv. As a default, read.table function sets headers to equal false, meaning that there are no column names and data starts from the first row of the data input. We typically work with data that has specified column headers, so we should set this to header equals true. Next, read.table needs to understand the type of separation used between the values. In the case of a CSV file, that is a comma. The final argument is strings as factors, which has the default setting of true. This means that if you have mixed data, for example, character and numeric data, that data would be set to factor. Therefore, we will set strings as factors to false. There are many other arguments that can be included in the read.table function, and references are provided if you would like to read further into them. However, these arguments discussed will cover most of the scenarios needed during PK analysis. So let's run the script and see what we get. The data is imported, and we can see the data set in the console. You may notice the column names appear rather strange and different to our original CSV file. It's best to avoid spaces and special characters such as parentheses, and as we've previously discussed, R is case sensitive, so we should keep that in mind when naming columns. Let's see what would happen if we don't include strings as factors argument. We renamed the columns to make them more manageable, and it appears as though the data are imported. However, when we want to see the class of data imported in time or concentration, conc, we will see that the data is imported as factors, meaning that further numeric calculations cannot be performed. Using the class function shows us that the time column in data is factor. At the same time, we can see the dose column contains integer data. If we try to perform a simple calculation with time data by adding the value 2, we can see the calculation is not possible for factorial data. It is possible to force the time column to behave as numeric, however. We see the results are not meaningful. It is more reliable to include strings as factors argument when reading in the data. I hope this has demonstrated that to you. We now see that the time column read in as character data. Again, we see that we're not able to perform numeric calculations with character data. However, we were able to force time data to behave as numeric and perform the addition successfully. You can see that R was not able to perform any calculation with the pre-dose time point. In further short lectures, we will cover manipulating data to allow pre-dose values to be set to 0 hours, and thus allowing further calculations and graphical analyses with the pre-dose time point. Manipulating data for further data summarization will be discussed later also. Read.csv is a function that will import CSV files. Unlike read.table function, the default argument in read.csv includes headers set to true, meaning that the default assumption is the first row of data are column names and that values are separated by a comma. So the command is a little shorter for read.csv. The first argument directs R to the data file, and we still want to include the strings as factors to be equal to false. If we call data, we're able to see how this data input into R. Using the names function, we can obtain the column names for our data. And we're able to assign a new list of column names by assigning a list of values to the right side. We need to be careful that we include the same number of names as columns of data that already exist in the data frame. This command sets the names of the data columns to equal dose, subject, time, and concentration, which are much more manageable in handling our data. The head function will list the first 5 rows of data in the dataset, and here we can see that we were successfully able to change the column names. Is.numeric asks if a particular set of data are numeric. First, we need to pull out the time column of the dataset, and we can do this by calling the dataset name followed by $ and the column name. In this case, data $time. In this case, we are asking if time column of data are numeric by using the function is.numeric and calling the time column using data $time in parentheses. So we can see the result came back as false, meaning the time column is not numeric. And this is because we have both character data listed as well as pre-dose, as well as numeric data for time points from 0.25 to 24 hours. Therefore, R will read this column as character. Let's check this using the is.character function, and we see that the time column is imported as character data type. We can force character data to behave as numeric using the as.numeric function. However, pre-dose values will be set to NA since R is not able to convert pre-dose, a character value, into a numeric value. And we can see this in the warning produced in the console. NA is introduced by coercion. Instead of forcing all time values as numeric, we are able to use an if-else statement to allow pre-dose values to be set to 0 hours and all other values to be set to numeric time values. This command states that if time equals pre-dose set to 0, else set to the numeric value of time. If the first condition is met, in this case time equals pre-dose, then time is set to 0. Else, time is set to the numeric value of the time column. Now we have converted pre-dose values to 0 and all other values to numeric. We can use the is.numeric function to determine if the time column is numeric, and we see the condition is now true. For graphical analyses, these pre-dose values will now be plotted to 0 hours. We could similarly set concentration values that are less than the lower limit of quantification to 0 nanograms per mil, which would allow samples below the limit of quantification to be plotted and also summarized. Common methods of handling samples which are below the limit of quantification include setting these values to 0. However, the true concentration likely lies somewhere between 0 and the limit of quantification, and this approach may lead to an underestimation of concentrations. Therefore, some pharmacokineticists prefer to set the value to half their limit of quantification. Regardless of the approach taken, consistency with the analysis is key, as well as pre-specifying the approach in an analysis plan for conduct of the final PK analysis. We can quickly and simply read in Excel files using the read Excel package. In R, we need to load the package, and that can be done using the require function, require read Excel. Next, to read in the data, we can assign the dataset name, data, or whatever the preference is, and read in using the function read_Excel, followed by the file name. Be careful that the file location is set to the same location as the working directory. Otherwise, you'll need to specify the file location exactly. Sas files are also simple to import with the read_Sas function. Typically, Sas datasets have .sas7bdat extension. To specify the file location, we need to check the location and copy and paste this here. We also need to convert single forward slashes to 2 forward slashes, or a single backslash, followed by the file name. The entire file path and name should be in quotes. This method allows you to pull data from multiple directories and includes this information in your R code to allow reconstruction of the analyses performed. You should now be able to import CSV, Excel, and Sas files from various locations on your computer. You should be able to review the types of data and understand how to handle mixed character and numeric data for reporting purposes. This short lecture provides a high-level introduction to importing and manipulating data. and I would strongly encourage you to read more on this topic of data manipulation.